Hello everybody, I'm Lup from sunny Singapore. In this presentation, I shall talk about a fun new emulator for Apache NetEx RTOS, the TinyEMU RISC-V emulator. If you would like to download the presentation slides, please head over to this link, lubyuan.github.io/netex. That's the letter L, not the digit 1. My presentation, transcript, articles, and source code are available at that link. What if we could boot and test NetEx inside a web browser? Today, we shall talk about the TinyEMU RISC-V emulator that runs in a web browser, how we ported NetEx to the emulator, and how we customized TinyEMU to emulate the aux64 single board computer by Pine64. TinyEMU is super helpful for running our daily automated testing of NetEx on aux64. We will find out how it works. How did we make NetEx run inside a web browser? Let us explore the internals of the TinyEMU RISC-V emulator. TinyEMU sounds like a tiny flightless bird, but it is actually a bare-bones RISC-V emulator for 32-bit and 64-bit RISC-V. It runs in a web browser thanks to WebAssembly. And yes, TinyEMU runs Doom. And since it runs Doom, what about NetEx? Can we boot NetEx inside a web browser with a little help from TinyEMU? We are looking at the live website for Apache NetEx RTOS. Click the link for online demo, and we will see NetEx booting right inside our web browser, all thanks to WebAssembly. This is a great way for anyone in the world to experience NetEx for themselves, right within their web browser. And yes, OS test works great too. This is proof that NetEx runs incredibly well on all kinds of devices, including web browsers. The demo we just saw is live on the Apache NetEx website. Try it here, or head over to the NetEx website and click Online Demo. How did we make this work? In this presentation, we talk about the HTIF console that is natively supported by TinyEMU and how we modified NetEx to support it. This is the Berkeley Host Target Interface, HTIF. For console input, TinyEMU supports Virtual I/O Console. We switch on the NetEx driver for Virtual I/O Console, which calls the OpenAMP library for I/O messaging. This is for Open Asymmetric Multiprocessing. Then we compiled everything from C into WebAssembly with the Enscripten compiler. Why are we doing this? Well, it is kind of fun to watch NetEx run inside our NetEx website. Like they say, eating our own dog food. Later, we will talk about emulating a real RISC-V single-board computer. This is the aux64 BL808 SBC by Pine64, which is super helpful for testing new NetEx apps and NetEx drivers. Maybe someday a NetEx dashboard that lights up and blinks in real time as the various NetEx drivers and NetEx apps activated. We could have done this in QEMU emulator, though it is a bit too complex to customize. TinyEMU is tiny, easy to modify, and runs in a web browser. To prepare TinyEMU emulator for modding, we download the C source code for TinyEMU, and we do the make. That is all we need. There is a demo of Linux booting on TinyEMU in case we need to figure out the internals of the emulator. We begin by customizing TinyEMU for the command line, then compile everything to WebAssembly later by calling the Enscripten compiler. We begin by setting the RISC-V system memory map in TinyEMU. TinyEMU is hard-coded to run at these RISC-V addresses. Yep, it is a very simple RISC-V emulator that doesn't have any fancy configuration files. We take NetEx for QEMU emulator for 64-bit RISC-V. We see that NetEx is already configured to boot at address 80 million hex, so no changes required to run on TinyEMU. How do we actually boot NetEx on TinyEMU emulator? We create a TinyEMU configuration file, which will start the 64-bit RISC-V emulator and boot it with our NetEx kernel. We try booting NetEx in TinyEMU, but nothing happens. Well, it didn't crash TinyEMU, which is a good thing. Remember that TinyEMU uses HTIF console, which NetEx knows nothing about. Let us teach NetEx to print something. NetEx is actually booting in TinyEMU emulator, but we can't see anything because NetEx doesn't understand how to print to the TinyEMU console. Let us help NetEx now. TinyEMU supports HTIF for console output. This is the Berkeley host target interface. HTIF comes from the olden days of the RISC-V Spike emulator. HTIF is a UC Berkeley standard, not a RISC-V standard. We don't see it much in other emulators. TinyEMU source code is surprisingly readable. Here is the code in TinyEMU that handles HTIF commands. To print the digit 1 to the HTIF console, we set the device to 1, command to 1, the buffer to 31 hex. We write this long value to the HTIF register located at this address, like this. Now we understand how HTIF console works. Let us print something in our NetEx boot code. Our NetEx boot code is in RISC-V assembly. Thus, we write this RISC-V assembly code to print to the HTIF console in TinyEMU. And we see 1, 2, 3. Yay! Indeed, NetEx is running on TinyEMU emulator. Okay, our NetEx boot code is printing something in RISC-V assembly. What about the UART driver in NetEx? Can we print the boot log and crash dumps? Remember we took NetEx from QEMU RISC-V, which runs on 16550 UART driver. Let us do a tiny tweak so that we will see something in TinyEMU's HTIF console. We patch the 16550 UART driver like this to make it print to HTIF console. What happens when we run this? We see NetEx booting OK on TinyEMU. Here is a NetEx boot log. But NHH shell doesn't appear. Why? Because NSH shell is a NetEx user space app that needs proper serial I/O with UART interrupts. In NetEx, serial output is buffered. It needs a UART interrupt to flush the buffer, which means NetEx will fill up the output buffer, wait for the transmit complete interrupt before sending more output. However, HTIF console doesn't support interrupts. Thus, we upgrade to a proper console with interrupts, Virtual I/O console. We have been doing console output with the HTIF console in TinyEMU. Won't it work for console input and NSH shell? Well, HTIF console supports polling of input and output, but it doesn't support interrupts. HTIF console is kind of bare bones, a bit like OpenSBI console. Polling only, no interrupts. To do proper console input and output with interrupts, we need Virtual I/O console. What is Virtual I/O? Virtual I/O is a standardized interface that allows virtual machines to access consoles, storage devices, and network adapters. And it works with TinyEMU. somewhat like RISCV semi-hosting, but a bit more sophisticated. What about virtual I/O on NUTX? Good news, virtual I/O is already supported by NUTX. NUTX provides virtual I/O drivers built with the Open AMP library. That's the library for Open Asymmetric Multiprocessing. Open AMP provides the message queue library for virtual I/O guests to call virtual I/O hosts by sending device messages. In this diagram, virtual I/O guest is NUTX, and virtual I/O host is TinyEMU. Open AMP sits in the middle. Now, how do we make NUTX talk to virtual I/O in TinyEMU? We look inside the TinyEMU source code. We see that TinyEMU uses these addresses for virtual I/O. We copy these virtual I/O settings to NUTX. With these settings in NUTX, the virtual I/O drivers and Open AMP library will start correctly on NUTX. This says NUTX has validated the virtual I/O magic number from TinyEMU, otherwise NUTX will halt with an error. Yep, NUTX has detected the virtual I/O console in TinyEMU, and the virtual I/O device is 3. The NUTX virtual I/O driver is talking OK to TinyEMU. Let us send some data to a virtual I/O console. To do that, we need 2 virtual I/O queues, the transmit queue and the receive queue. This is how we create the virtual I/O queues in NUTX kernel. Transmit queue and receive queue. We will message these queues, which will print to the console. But isn't there already a virtual I/O console driver in NUTX? Yeah, NUTX has a virtual I/O serial driver, but we will do it ourselves anyway, so we can learn the inner workings of virtual I/O and Open AMP. To print something, we send a message to the transmit queue, like this. Our code prints successfully in TinyEMU. All these virtual queue functions, they come from the Open AMP library. So virtual I/O in NUTX is tightly integrated with the Open AMP library. Now we understand virtual I/O and Open AMP a little better, we can switch back to the virtual I/O serial driver that is already in NUTX. We are almost done with NUTX for TinyEMU Emulator. Here are the remaining bits that we completed. We switch over to the official NUTX driver for virtual I/O serial, which will support console I/O with interrupts. For RISC-V interrupts to be triggered correctly, we set the PLIC address in NUTX. That's the platform level interrupt controller. We will keep the HTIF console, but only for printing debug messages during NUTX startup. There is something odd about RISC-V interrupts in TinyEMU. Somehow, TinyEMU won't let us enable MEIE, machine mode external interrupts. Our workaround is to enable SEIE, supervisor mode external interrupts. Then we patch the NUTX exception handler and map the interrupts from supervisor mode to machine mode. Nothing appears when we type in NH shell. Why? That is because we haven't enabled the echoing or key presses. Here is the fix. This will echo all keys pressed, and if the key press is carriage return, convert it to line feed. With these final few fixes, NUTX boots on TinyEMU Emulator all the way to NSH shell. We compiled TinyEMU from C to WebAssembly with the Enscripten compiler. Today it is live on the Apache NUTX website. Try it here, or head over to the Nutex website and click Online Demo. We haven't upstreamed the TinyEMU port to Nutex mainline. Let me know if you can help. This is a fun, impactful way to create something useful that anyone in the world can use by clicking the Apache Nutex website. If we look back at Nutex for TinyEMU emulator, we tweaked Nutex to run on TinyEMU, which is kind of backwards. Why not tweak TinyEMU to emulate a real Nutex device? Then we can run Nutex on TinyEMU without any changes. Now we talk about TinyEMU emulating a real RISC-V single-board computer, the AUX64 SBC by Pi64, based on the Buffalo Lab BL808 SBC. This means we shall port Nutex for AUX64 directly in our customized TinyEMU emulator, without any changes to Nutex for AUX64. We have a huge presentation on Nutex for AUX64 SBC. Please check out the presentation at this link. Today we shall chat about emulating the AUX64 SBC with a customized version of TinyEMU emulator. Here is a quick peek of AUX64 emulator. It runs the same way as the TinyEMU emulator on Nutex website, except that we customize TinyEMU to emulate a real AUX64 SBC, and it will boot Nutex for AUX64 without any modifications, which is a terrific way to test new Nutex drivers and apps. Now we go into the details, how we customize TinyEMU emulator to emulate a real AUX64 SBC. First thing we tweak in TinyEMU, the system memory map for AUX64 SBC. TinyEMU is hard-coded to run at fixed RISC-V addresses. Thus, we change these addresses to match the Buffalo Lab BL808 SoC. This part looks similar to the earlier slides, but instead of tweaking Nutex to run on TinyEMU, now we tweak TinyEMU to run Nutex. See the difference? The TinyEMU boot code is located at this address, 10,000 hex. It jumps to the Nutex kernel at startup. We will customize this for AUX64 SBC. Remember that TinyEMU supports Virtual I/O console. This won't work with the AUX64 SBC. TinyEMU needs to emulate the BL808 UART controller inside AUX64. We dig around the BL808 SoC and we discover these UART registers. We write to this UART register to print a character to UART output, and we read this UART register to check if UART transmit is ready for more output. This means that TinyEMU needs to intercept these UART addresses to emulate the BL808 UART controller. Inside TinyEMU, we intercept all reads to this UART register address and writes to this UART register address. That is how we pretend to be a UART port. More details coming up. This is the address of the UART status register. Nutex will read this UART register to check if UART controller is ready to transmit more output. In TinyEMU, we intercept all reads to this address and return the value 32. Why 32? That is the UART buffer size for BL808 SoC. It sounds simplistic, but it works for now. This is the address of the UART output register. Nutex will write to this UART output register to print a character to UART output. In TinyEMU, we intercept all writes to this address and we print the character that's written to the address. Don't forget the UART interrupts, which will be managed by the PLIC, Platform Level Interrupt Controller. To handle UART interrupts, we emulate these UART registers. UART status register should say there's UART input. UART interrupt mask should return 0. UART clear interrupt should clear the interrupt. UART input should return the key press. And we are done with UART. When we boot aux64 NUTX on TinyEMU, we will see the UART interrupts handled correctly by the platform level interrupt controller. TinyEMU boots NUTX in RISC-V machine mode, but we need TinyEMU to boot in RISC-V supervisor mode. Let us figure out how. What exactly is this boot code in TinyEMU? Think of it as BIOS for booting a computer. TinyEMU needs a tiny chunk of RISC-V machine code that will jump to a NUTX image in RISC-V machine mode. This won't work for aux64. We will find out why. TinyEMU is a bare-bones RISC-V emulator. It boots in only one mode, RISC-V machine mode, which is the most powerful mode in the RISC-V system. But NUTX for aux64 won't work in RISC-V machine mode. It expects to run in RISC-V supervisor mode, which is one level less powerful than machine mode. Why supervisor mode? That is because RISC-V SBCs, like aux64, will boot OpenSBI in machine mode. This is the supervisor binary interface. It is like BIOS for RISC-V. OpenSBI then boots the NUTX kernel in supervisor mode. Okay, technically OpenSBI boots the U-boot bootloader followed by the NUTX kernel. This means we need to tweak TinyEMU to boot NUTX in supervisor mode instead of machine mode. And we don't have OpenSBI in TinyEMU, so our BIOS for RISC-V is kind of absent. Hence, we emulate OpenSBI in TinyEMU, just the bare minimum of OpenSBI that is needed by NUTX, like for handling system timers. Remember the TinyEMU boot code we saw earlier? It boots our NUTX kernel in machine mode. Now we modify the TinyEMU boot code so it boots NUTX in supervisor mode. First, we dedicate all exceptions and interrupts so they get forwarded to NUTX in RISC-V supervisor mode instead of machine mode. Otherwise, exceptions and interrupts will whoosh by and bypass NUTX altogether. We are about to jump to NUTX kernel in supervisor mode. The way we do this is rather roundabout. First, we set the previous privilege level to supervisor mode, and we can execute an mret return from machine mode that will jump to the previous privilege, which is supervisor mode. We solve our headache. TinyEMU boot code now boots the NUTX kernel in supervisor mode. What about the RISC-V system timer? How do we emulate OpenSBI so that system timers will run correctly on NUTX? RISC-V system timer can only be set in RISC-V machine mode. NUTX runs in RISC-V supervisor mode. That is why NUTX expects to call OpenSBI to start a system timer through an eCall system call that will jump to machine mode. To emulate OpenSBI, our modified TinyEMU will intercept the eCall made by NUTX and set the system timer for RISC-V machine mode. NUTX expects to read the system time through the time CSR register, like this code from NUTX kernel. CSR means control and status register, controls a RISC-V system. We have a problem. The time CSR register doesn't exist in TinyEMU. Thus, we emulate the register in TinyEMU. At startup, we search for all RD time instructions. We patch RD time to become an eCall system call, and TinyEMU will emulate the eCall to return the system time. We have a few more steps to emulate the system timer. I won't cover the details today. Please check out these links. We talked about emulating the time CSR register because TinyEMU doesn't support it. Is there anything else that TinyEMU can't handle? Yep, inside the BL808 SoC is the T8C906 CPU. NetEx for aux64 will call these special RISC-V instructions to flush the MMU cache for the C906 RISC-V CPU, dcache.il and sync.s, which come from the T8C906 extensions and won't work in TinyEMU. Thus, we patch these special RISC-V instructions to become eCall system calls, so they won't crash the TinyEMU emulator, though we don't emulate the instructions right now. We talk about these special RISC-V instructions in my presentation on aux64 SBC. Please check it out at this link. Our aux64 emulator works great for emulating the UART controller and GPIO controller inside aux64 SBC. Here, we run the QuickJS JavaScript engine on aux64, which will blink a simulated LED connected to our emulated GPIO controller. We have a presentation that explains how we ported JavaScript to NetEx. Please check out the link below. We wrap up today's presentation with a super helpful way of using our aux64 emulator. That is for daily automated testing of NetEx on aux64. Let us walk through the implementation of the automated testing based on expect scripting and TCL. Yes, the good old scripting language. This gets triggered every day by GitHub Actions and alerts us via email if the daily test fails, which is terrific for NetEx regression testing. What exactly is an expect script? With an expect script, we can feed our commands automatically into the emulator. Here is an expect script that sends the uname command to our aux64 emulator. If the NHH prompt is missing, or if the uname command takes too long to execute, this expect script will fail. Our expect script runs automatically like this. Will it work for complicated tests? Yep, that is the beauty of TCL scripting. We may use pattern matching and timeout detection in our script. It works really well with OS tests for testing everything in NetEx. And this is exactly what we do every day at GitHub Actions. Run OS tests on aux64 emulator and fire us an email if OS test fails on aux64 emulator. How thorough is OS test for testing everything in NetEx? Super thorough. Last we checked, these are the NetEx tests executed by OS test. Today, OS test has probably added a few more NetEx tests. Running daily automated tests on aux64 emulator is probably the next best thing to running daily tests on a real aux64 SBC, which we might try next. One final word on emulators. Recently, I'm so hooked on running good old games, Pac-Man, Collection, Street Fighter, on the retro gaming emulator like RetroArch, which got me thinking. RetroArch will actually emulate a couple of interesting architectures like ARM32, Z80, X64. What if we could run NetEx on RetroArch? Then we will have NetEx on RetroArch on iPhone, iPad, and Apple TV. As we ported NetEx to TinyEMU and created the aux64 emulator, we wrote plenty of detailed notes. Check out the articles here. We have 2 more presentations on AUX64 SBC about porting NUTX to AUX64 SBC and the analysis of real-time logs from AUX64. Please check out the presentations at this link. The great news, our NUTX website now runs NUTX. Anyone in the world can click into our website and try out NUTX for themselves. We created an emulator for AUX64 SBC that is super helpful for automated daily testing and regression testing. Maybe we can create more emulators for NUTX devices and make NUTX development a little easier. Thank you.